Welcome to today's presentation. This slide is titled, "The Puzzle That Started It All," and it really captures the essence of how everything began. What we're looking at here is the initial challenge or mystery that sparked our journey. It's important to understand that this puzzle wasn't just a simple problem. It was a catalyst that pushed us to think creatively and explore new solutions. This moment of discovery is what set everything in motion, leading us to the insights we'll discuss later. By focusing on this starting point, we can better appreciate how curiosity and persistence drive innovation. It's a reminder that sometimes the biggest breakthroughs come from the simplest, yet most intriguing questions. This puzzle served as the foundation for everything that followed, and understanding it helps us see the bigger picture of our overall mission. Let's explore the core insight here. From numbers to operations. What does that really mean? Well, it's about shifting our focus from just looking at raw data or numbers to understanding how those numbers translate into meaningful actions. Essentially, it's not enough to simply observe the data. We need to interpret it in a way that informs our decisions and strategies. This transition is crucial because it helps us connect the dots between what we see and what we do next. It's about turning insights into operations, applying what we've learned in a practical way. That's the key to leveraging data effectively and making smarter, more informed choices in our work. By embracing this mindset, we're aligning our analytical tools with real-world applications, which ultimately drives better results and continuous improvement. This shift from numbers to operations is at the heart of transforming data into value within our overall approach. Let's take a closer look at the 3 pillars of operational cyclicity. These pillars are fundamental to understanding how operational processes can be optimized over time. First, we have the concept of stability, ensuring that our operations are consistent and predictable. Stability provides the foundation for efficient planning and resource allocation. Next is flexibility, which is about adapting to changes and uncertainties without losing momentum. Flexibility allows us to respond quickly to market shifts or unexpected challenges. Lastly, we have sustainability, emphasizing that our operational cycles should be sustainable in the long run, balancing short-term performance with long-term viability. Together, these 3 pillars, stability, flexibility, and sustainability, form the core that supports a resilient and efficient operational cycle. Connecting these points to the overall theme, it's clear that mastering these pillars helps us create a more responsive, reliable, and sustainable operation in a constantly changing environment. Let's take a closer look at how we formalize this framework. First, this step is crucial because it provides a clear structure for our ideas and concepts. By formalizing, we mean converting our ideas into a set of well-defined models or rules that can be consistently applied. This helps us ensure clarity and precision in our analysis. Next, we want to highlight the key points, such as the importance of defining variables clearly, establishing logical relationships, and setting boundary conditions. These are the building blocks that make our framework robust and reliable. Connecting this to the overall theme, formalizing the framework allows us to move from abstract ideas to concrete, actionable methods. It's what enables us to systematically evaluate different scenarios and draw meaningful conclusions. So, in essence, this step anchors our entire approach, making sure everything is grounded in a solid, logical foundation. Let's take a closer look at the decomposition choice problem. This is a critical concept because it highlights the challenge we often face when trying to break down complex problems into manageable parts. Essentially, the problem involves deciding how to decompose a task or a system in a way that makes it easier to analyze or solve. The key point here is that the way we choose to decompose can significantly impact the effectiveness of our solution. If we break things down too granularly, we might lose sight of the big picture. If we go too broad, we might end up with a solution that's still too complex to handle efficiently. This problem is central to our overall theme because it touches on the balance between simplicity and comprehensiveness in problem solving. The better we understand how to make these decomposition choices, the more efficient and effective our approaches will be. So, mastering this problem helps us optimize our strategies and ultimately leads to better outcomes. Let's look at some case studies that illustrate how different numbers can lead to different cycles. What this shows us is that each situation is unique, and the numbers involved can significantly influence the pattern or cycle we observe. It's important to recognize that even small variations in data can create distinct outcomes, which is why understanding the context behind the numbers is so crucial. These examples help reinforce the idea that while patterns might seem similar on the surface, the underlying variables often differ, impacting the overall cycle. Connecting this back to our main theme, it underscores the importance of analyzing the specific details in every case to accurately interpret cycles and predict future trends. Let's take a closer look at the discovery methodology. This slide highlights how we approach uncovering key insights and understanding the problem space. First, we start with thorough research, which involves gathering data from various sources to get a comprehensive view. Next, we engage in stakeholder interviews and workshops, allowing us to collect diverse perspectives and identify hidden needs. We also use observational techniques, like shadowing users, to see how processes work in real life. Combining these methods helps us build a complete picture. Importantly, our methodology is iterative, meaning we continuously refine our understanding based on new findings. This approach ensures that our solutions are grounded in real-world insights and aligned with overall project goals. It's a crucial part of our process because it sets the foundation for effective problem-solving and innovation. Let's take a closer look at the cyclic classification, which we can think of as the periodic table of numbers. On this table, each number is associated with a minimal pipeline, a length, and a strength. For example, the number 1 has the simplest pipeline, just a single multiplication operation, and it's considered strong in terms of its robustness. The number 4 also has a relatively simple pipeline involving addition, a constant, and multiplication, and it's also strong. Moving to 6, we see a slightly longer pipeline with more steps, adding, multiplying, and constants, making it medium in strength. Then there's 7, which requires a much longer 14-step pipeline, and as a result, it's considered weak because of its complexity. Finally, the number 9 has a pipeline involving addition, constants, and summation, with a length of 3 steps, placing it in the medium category again. The key takeaway here is that the complexity of the pipeline and the operations involved influence the strength and classification of these numbers. This cyclic view helps us understand how different numbers relate to each other based on the minimal steps needed to generate or classify them, tying back to the overall theme of understanding number relationships through their pipelines. Let's take a closer look at this slide titled, Visualizing the Landscape, the Cycle Graph. Here, we're focusing on how the cycle graph helps us understand complex systems by illustrating recurring patterns and continuous processes. You see, the cycle graph is a powerful visual tool because it emphasizes the cyclical nature of many phenomena, whether in ecosystems, business processes, or even social behaviors. It shows how different stages or components are interconnected in a loop, creating a seamless flow from start to finish. What's really important to grasp is that this visualization helps us see the bigger picture, how each part influences the next, and how the entire cycle sustains itself over time. It's about understanding the rhythm and momentum within a system, which is vital as we think about managing or optimizing these processes. Connecting this to our overall theme, the cycle graph underscores the importance of seeing systems holistically. Instead of isolated steps, we're viewing a continuous loop, which is essential for identifying leverage points or potential areas for intervention. So, by visualizing the landscape this way, we gain insights that are both strategic and practical, enabling us to better anticipate changes and foster resilience within the systems we study. Let's explore some intriguing new research questions arising from number theory. For instance, do prime numbers have characteristic cyclic signatures that can help us identify or categorize them? We might also ask, what is the minimal cycle length for each number, and how does that relate to their properties? Additionally, are there certain patterns shared among specific number families, like squares or palindromes? This leads us to consider whether there are universal pipelines that apply across multiple numbers, revealing deeper connections. And of course, how does the strength of these cycles relate to other properties of numbers? Now, shifting to the concept of behavioral mathematics, rather than focusing solely on what numbers are, we classify them by what they do, how they respond to different operations and transformations. This idea of transformational fingerprinting is key. Each number responds uniquely to a set of operational pipelines, creating a distinctive mathematical signature. This approach opens up exciting potential applications. For example, in number classification, it offers a new way to categorize integers based on their behavioral responses. In cryptography, these signatures could enhance security by providing new patterns to recognize or generate keys. For AI training, this rich dataset of behaviors can improve machine learning models. It also offers innovative educational tools, interactive ways for students to explore numbers dynamically. And finally, from a theoretical perspective, this perspective can provide fresh insights into long-standing questions in number theory. Overall, this approach encourages us to see numbers not just as static entities, but as dynamic systems with unique behaviors, opening up new avenues for research and application. Artificial intelligence and exploratory mathematics are really fascinating areas that are transforming how we approach problem-solving and discovery. Here, we're seeing how AI can serve as a powerful tool to explore complex mathematical concepts that might be difficult or time-consuming to analyze manually. The key point is that AI isn't just about automation. It's about augmenting our ability to understand and generate new mathematical ideas. Through machine learning algorithms and data-driven approaches, we can identify patterns, test hypotheses, and even uncover relationships that we might not have noticed otherwise. This ties into the overall theme of the presentation, which is about harnessing technology to enhance our learning and exploration. By integrating AI into mathematics, we're opening up new pathways for innovation and discovery, making mathematics more accessible and dynamic. So, in essence, AI acts as a collaborator in exploration, helping us push the boundaries of what we can achieve in mathematics and beyond. Let's explore the philosophical foundations behind redefining mathematical truth. Traditionally, we think of mathematical truths like 2 + 2 = 4 as absolute, static, and independent of context. These are what we call classical mathematical truths, which are fixed and unchanging, no matter how or where you look at them. But in more modern, process-oriented approaches, we see a different picture. Think of operational mathematical truth, like T of 7 = 7. This perspective emphasizes that truth can be contextual, process-dependent, and pipeline-specific. It depends on the particular way we're examining or transforming the number. Now, the key insights here are quite profound. First, the idea of multiple truths, meaning a number can be true in several different pipelines, depending on how we're analyzing it. Second, each pipeline reveals a different aspect of a number's behavior, so we're uncovering different truths depending on the process we're using. This leads us to the concept of active mathematics, which shifts our focus from static objects to dynamic processes and transformations. Instead of seeing numbers just as fixed entities, we view them as active, behaving differently depending on the context. Ultimately, this behavioral perspective encourages us to see numbers as dynamic entities with patterns of behavior, not just static points. Moving from static objects to dynamic processes helps us better understand the richness and complexity of mathematical truth in a modern, interconnected world. Let's take a moment to look at the community project, Cyclopedia. This initiative is a great example of how community engagement can be harnessed to promote cycling awareness and education. The project focuses on creating comprehensive resources, like guides and maps, that help both new and experienced cyclists navigate their local areas safely. It's about building a stronger, more connected community around cycling. What makes Cyclopedia particularly impactful is how it encourages collaboration, bringing together local organizations, volunteers, and residents to contribute and share knowledge. This aligns perfectly with our overall theme of fostering community-driven solutions that promote sustainability, health, and inclusivity. By supporting projects like Cyclopedia, we're not just promoting cycling. We're empowering communities to take ownership of their transportation choices and work together toward a healthier, more sustainable future. Now, let's look at the grand conjectures that form the core of this exploration. First, we have the weak operational cycle conjecture, which suggests that for every natural number n equal to 1, there exists at least one finite operation pipeline, t, such that when we apply t to n, we get n back. Essentially, this means that for each number, we can find a sequence of operations that loops back to the original number, highlighting a kind of cyclical behavior in these operations. Moving on, the strong operational cycle conjecture takes this idea further. It proposes that there's a universal pipeline t that works for all natural numbers n, in other words, a single, overarching sequence of operations that can be applied to any number and still produce a cycle. If proven true, this would be a groundbreaking insight into the universality and structure of these operational systems. Next is the minimal cycle conjecture. This one states that for every n, there's a pipeline of minimal length that forms a cycle. So not only do cycles exist, but there's an optimal, shortest possible sequence of operations that brings n back to itself. Understanding these minimal cycles could reveal the most fundamental repetitive structures in these systems. Then we have the complexity conjecture, which suggests that as n increases, the complexity of these minimal cycles becomes unbounded. In other words, larger numbers may require increasingly intricate or lengthy pipelines to form a cycle, hinting at deep complexity in the underlying mathematical landscape. Now, why are these conjectures so significant? They could become what we might call the Fermat's last theorem of operational mathematics, simple to state, but with profound and far-reaching implications. If we can prove or disprove these, it could reshape our understanding of these systems. Of course, there are substantial research challenges ahead. We need to develop new proof techniques tailored for these operational systems, connect these ideas to computational complexity, and explore their relationships with established number theory. Building computational verification systems will be crucial, as will the creation of new mathematical frameworks to understand these phenomena better. Finally, I want to leave you with an open invitation. These are fundamental claims that remain unproven. Whether you're a mathematician or a researcher, I encourage you to try to prove or disprove these conjectures. Your work could be pivotal in unlocking new frontiers in mathematical understanding. Research program and call to action. This slide really emphasizes the importance of our research program as a foundation for advancing the field. It's not just about conducting studies, but about creating a structured approach that drives innovation and meaningful change. And the call to action is crucial. It's a reminder that everyone has a role to play. Whether you're a researcher, a stakeholder, or a supporter, your involvement can make a real difference. So, as we move forward, I encourage you to think about how you can contribute to this effort. Together, we can turn these insights into impactful solutions that benefit the entire community. This is our opportunity to make a lasting impact, so let's stay engaged and proactive. As we look ahead, I want to talk about the journey that lies in front of us. We started this exploration with a simple observation, just a curious numerical sequence involving the number 7. It might seem small, but that initial curiosity opened the door to something much bigger. What we've uncovered is essentially a new mathematical landscape, one where numbers aren't just static entities, but reveal themselves through transformation. It's like exploring a hidden world where each number has a story to tell, if we know how to read it. Now we're standing at the frontier of this exploration. We're ready to map out the behavioral patterns of integers, understanding how they behave, change, and relate to each other within this new context. The territory is full of potential, waiting for us to discover what lies beneath the surface. The tools we need are already in our hands, our curiosity, our methods, and our analytical skills. And so, this is where the adventure begins, right now. We're on the brink of uncovering new insights that will deepen our understanding of numbers and their hidden patterns. It's an exciting moment, and I'm thrilled to see where this journey takes us next. Join the exploration, everyone. As we come to the end of this presentation, I want to emphasize how important it is to stay curious and engaged. This is an open invitation to continue discovering, learning, and growing beyond what we've covered today. Remember, exploration is a continuous journey, not just a one-time event. Whether it's applying new ideas, experimenting with different approaches, or simply asking more questions, every step you take is part of that bigger picture. So I encourage you to embrace this mindset. Stay curious, keep exploring, and be proactive in seeking out new opportunities. That's how we truly make progress and create meaningful change. Thank you for being part of this journey with me.